Hello everybody, and welcome to part 6 of Infinite Series. This is the final chapter. It's kind of like that Star Wars movie that was the final one. Really, it was only like the third one. Yeah, like that. Okay, so in this series of the series, hi Feynman, we are going to talk about whether or not a series converges. And if it converges, we'll talk about on what interval it converges, like for what values of x. Right now, we can only do that for geometric series, but in this section, we want to be able to do it for all series. I am going to break this into a couple videos. I actually already recorded it once, and it was so freakishly long that I couldn't even watch it back myself. So I'm going to break it into a couple. So nobody needs to hear me talk for that long. Okay, so when we are talking about convergence of a power series, when we're talking about convergence in general, there's really two kinds of series that we can be dealing with. The first kind of series is the one like a geometric that only has an n in it. There's no x's in it, right? And if it only has an n in it, then the answer is either yes, it converges, or no, it diverges, right? When we talk about the convergence of a power series is going to have n's in them, but also x's, because remember, when we write a power series, a Taylor series, it ends up looking like a big fat polynomial. So whether or not it's going to converge is going to depend on the value of x. Right? Some of them will only converge if x is small, some of them will converge everywhere. Like sine x converges, the series for sine x converges no matter what x is, but not all series are going to be like that. Okay, so when we're talking about a series, a power series that has both an x and an n in it, it's really going to be very dependent on the value of x, and that's where this interval of convergence comes in. All right, so this series right here, x over n factorial, that is going to converge no matter what the value of x is, right? Factorial grows so quickly that no matter what the value of x is, eventually this factorial is going to take over. These terms are going to very quickly go to 0, and this thing is going to converge. So for this, its interval of convergence is just going to be every value of x everywhere. This just straight converges no matter what. Then we have a series like this where the terms are going to get bigger and bigger and bigger. Regardless of how small you make x, the terms are still going to get bigger and bigger and bigger. So this series is going to diverge no matter what. The ones that are going to take us a little more energy to deal with are this last kind, where this actually is a geometric, right? It's just a power, a repeated addition of x. We have to figure out where it's going to converge. So it's like on what interval. So we know that since this is geometric, it's going to converge between -1 and 1. But one of the other things we have to look at in this section is, outside of a geometric, of course, can we include the -1 and the 1? Like, is my interval of convergence -1 to 1, or is it this? Or is it like you can include the -1 but not the 1? Right? So we'll have a little bit of work to do on that as well when it comes to intervals of convergence. Right. But before we go into that, I want to talk a little bit more about how we find an interval of convergence. This is literally just a set of x values, but instead of listing them, right, we give the interval. And we know a few things about an interval of convergence. We already learned that it's always going to be symmetrical around the center. That's happening, right? So visually, that's kind of, I try to make a visual here, like this is your all real number line, right? This green line right here is going to be the center of your series. So if you centered your series at 0, it's going to be symmetrical on 0. If you centered your series on 5, it's going to be symmetrical on 5. Now, new to us is this. It's called the radius of convergence. Radius is usually reserved for circle things, but not here. The radius of convergence is literally just how far from the center you can go and still have convergence, right? So we said that polynomials get better and better and better the longer they are, but the further you move from the center, as you move away from the center, your approximation kind of gets less and less accurate. So there's only so far you can go from the center and still have convergence, right? That distance the distance from the center to the edge of your interval convergence is called your radius of convergence. So this whole interval of convergence, of course, is like the diameter of convergence. No, it's not. It should be, though. It's called the interval of convergence, right? So, but again, it's this is a radius of convergence and this is a radius of convergence. So it's always going to be symmetrical on either side of the center. Okay, so let's take a look at just a couple examples of how we would write a radius of convergence and an interval of convergence. So if you have a series that converges only at the center, and they're telling us here that the center is 2, we would say that the radius of convergence for this series is 0 because it only converges at the center. So if this is my center, I can't move anywhere. I can't go to the left. I can't go to the right. I can't do anything. So my interval of convergence is literally a single digit, 2. If you have a series that converges at the center, and in this case the center is 4, and some finite interval around the center, that's like the picture we just saw on the last slide, right? So here's your center, which is 4, and you can go some distance this way, we'll call it R, and you can go some distance this way, we'll call it R. So this is going to be your interval of convergence, right? So they didn't give us an interval of convergence here, but if we found an interval of convergence, let's say it was, I don't know, 5, then we would say R is 5 or whatever. Okay, now you should be able to give an interval here, like an actual interval. The way you would do that is do 4 plus your radius of convergence to get your upper limit, and then 4 minus your radius of convergence to get your lower limit. Okay, so again, for example, let's say we found that our radius of convergence was 5, my interval would be from -1 to 9. And then I could look back on that if I needed to and know that the center was 4, even if they hadn't told me. In a problem, if they give you the interval, you can know that the center is right in the middle. It is worth noting at this point that we are not going to include either endpoint for now. Notice I left open brackets here. We will eventually look at whether or not to include those endpoints, but we pretty much have to finish this whole section, and that'll be like the last thing we do. So for right now, don't include them just to be safe, and then we'll decide later if we can include them. Okay, last possibility here is that a series converges only at the center, or I'm sorry, converges at the center and converges everywhere else. Like this is your series for sine, your series for cosine, your series for e to the x. They converge everywhere. So if that's the case, your radius of convergence is infinity. And you can either say that your interval is all real values, or you can say that your interval, is negative infinity to infinity. I will just note again, do not ever, 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 ever include infinity. It's not a number, it's an idea. You cannot include it in an interval, ever, not just for series. All right. I meant to mention at the beginning of this video that if you have not printed your flowchart, that you should definitely do that because you're going to want to use it to take notes on this video. So if you have not yet printed that flowchart that I told you to print in the assignment, pause this video and go print that flowchart, because what you're going to see throughout this video is snips like this, and you're going to want to fill in your flowchart. The AP is open note, open book this year, so you're going to want to have something like this in front of you. I cannot tell you how many times I've had kids call me from college and ask for this. Literally just last week, a kid I had a solid 10 to 12 years ago emailed me. He's in a PhD program in New York, the city. My mind is absolutely blank right now. City University of New York or City College of New York or something. And he was like, you remember that flowchart you gave us? I need a copy. This is amazing. People have been asking me for years to use this on the AP, and I always say, no, of course you can't use it. Like guess what? You can use it. All right, so get it, print it, take good notes on it. Up here in the upper left-hand corner where it says, is it geometric? That's your start. right? That's the first question you ask yourself anytime you see a series. Is it geometric? Because if it's geometric, not only do I know if it converges, but I know what it converges to. So if the answer to is it geometric is yes, we're going to this bubble. And in that bubble, it's going to converge as long as the absolute value of r is less than 1. Right? So not that you need that written down because you already know that, but when the absolute value of r is less than 1, as long as r is between -1 and 1, it's going to converge, and it's going to converge to a over 1 minus r. All right, that is best case scenario that you get a geometric. If you do not get a geometric, the next place we go is right here. The question is it a p-series? A p-series is any series very generically in this form 1 over x to the p. Now, it doesn't have to be an x. If a series is 1 over n to the 5th, that's a p-series, right? The variable doesn't have to be an x. The variable could be anything. Okay. But if it's as simple as that, like 1 over a power of your variable, it's considered a p-series. Now, technically, if it's like 2 over n to the 5th, is it a p-series? Technically not, but we'll talk about that in a minute. Okay, so if the answer is yes, it's a p-series, as you can see, I already fumbled and made this come up. Okay. As long as p is greater than 1, you have a series that converges. Okay. So for example, the series 1 over n squared, that converges, it's a p-series. The series 1 over the square root of n, that diverges because that's an n to the 1/2, which is less than 1. So for a p-series, they're pretty easy to recognize. As long as your exponent is greater than 1, you have convergence. If your exponent is less than or equal to 1, you have divergence. Okay, so a couple things on p-series. Number 1, like I was saying before, if you have something like this 2n to the 5th, if 1 over n to the 5th converges, that means that this series is going to come out to be some finite number, right? So if you have 2 over n to the 5th, if you have that series, one could argue that that's like having 2 times the series 1 over n to the 5th, right? So 1 over 1 to the 5th plus 1 over 2 to the 5th plus 1 over 3 to the 5th, blah, 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 blah. Point being that if this is a finite number, then obviously when you multiply it by 2, it's still going to be a finite number. So I am sure somewhere there are mathematicians that would say that's cheating, but I don't really care. Neither does the AP. It's not really a big deal. The other thing that comes up for me here is that there is a very special series called the harmonic series. And we've already seen it. Okay, the harmonic series is 1 over n. Simple as that. Starting at n equals 1. Because I can't write down here. Okay, so the harmonic series looks like 1 plus 1/2 plus 1/3 plus 1/4. And if you actually start doing partial sums of this series, it starts looking a heck of a lot like it's going to converge. But once we know about the p-series, we know it's going to diverge. Okay, so the harmonic series is a very popular series. We see it a lot. You can literally just say harmonic series diverges. Okay. Now, if you have a series 1 over n to the 1.01, convergence. But that guy, that harmonic series, he diverges. He's like the last in line to diverge in the ones of that form. Okay. This is my great joke for this. I don't know if you guys saw this movie. It was called Divergent. Get it? I put the harmonic series in there instead of Divergent. was like not that good. Tried to be the Hunger Games. Yeah, the Hunger Games. Okay, let's take a look at this series. And let's go through our flow chart. Don't skip over the geometrics. Is it a geometric? No, it is not. Is it a p-series? Yes, it is. So it is a p-series. This exponent right here is greater than 1. So we can say that this series converges. And then we give our reason, p-series, p greater than 1. Done. Okay. If you're going to say a series converges, you have to say what test you used. So this was a p-series with p greater than 1. That's convergence. Done. Okay. This one. This one is a p-series, but it looks a little suspicious at first. Right? In order to become or look like a p-series, we have to do a little rewrite here. So in the denominator there, you have both an n and a square root n, but you can think of that as an n to the first and an n to the 1/2, and then that suddenly becomes 1 over n to the 3/2. Okay. Once it's written like that, 3/2 is bigger than 1. So again, we have converges, p-series, p greater than 1. Okay, this guy. Don't skip the question. Is it geometric? It is. Again, it's trying to be sneaky. It's trying. E to the n over 2 to the n is the same as e over 2 to the n. That's geometric. Okay, and there's your r right there, e over 2. So this is geometric. R equals e over 2. So here's the part where they try to trick us. E over 2 is a fraction. So one might think, oh, it's a fraction, it's less than 1. It's not. E is bigger than 2. So e over 2 is bigger than 1. So we're going to say diverges because the absolute value of r is greater than 1. Wah, wah. But it's a really quick way to answer those questions. Okay, so if it's geometric, awesome, you have a very quick answer. If it is not, and it's p-series, not as good as geometric, but it gives me a convergence divergence answer. Okay, if neither of those work, if it's not geometric and it's not a p-series, the next place we go is to this nth term test. Now the nth term test has a nickname, and it is called the divergence test. Now, I think that's a great nickname for this test. And here's why I think that. This test is only good for proving divergence. Okay? It's only good to prove divergence. In other words, there should never be a moment where you say, this converges and my reason is nth term test. Okay, here's why. What the nth term test asks is, are the terms approaching 0? So if the terms are approaching 0, pretty much we don't know anything. Case in point, this stinking harmonic series. Always the 1, right? That's 1 plus 1/2 plus 1/3 plus 1/4, blah, 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 blah. The terms are approaching 0. It's not converging. Okay? People tend to think that this test is like, oh, as long as the terms are approaching 0, that's convergence, moving on. No, they can be approaching 0. They have to be approaching 0 fast enough. And you don't get to pick what's fast enough. Math picks. I'm going to pause this video for a minute because there is a stink bug crawling like directly in front of me. It's kind of grossing me out. Excuse me for a moment. Back in business. Okay. Where was I? Oh, all right. So, if the terms are approaching 0, this test is just a big fat fail. Sorry. If the terms aren't approaching 0 though, if the answer is no, these terms are not approaching 0. So for example, look at this series. 1 plus 1.1 plus 1.01 plus 1.001. We can clearly see a pattern here, but my terms aren't approaching 0. My terms are approaching 1. Well, when you start adding all these terms up, that's going to go to infinity. I mean, it is. It's going to look, as you're not adding tiny numbers, you're adding very finite numbers. And so when you add an infinite number of them, it's going to go into infinity. So if you see a series like this, it's not a p-series, it's not a geometric series, but it is, we can knock that out with nth term. The terms are not approaching 0, so we would say it diverges by the nth term test. Okay, so boom, diverges. If they're not approaching 0, it diverges. Okay, so those 3 are like the quick 3 right at the beginning. You ask those 3, they're all really fast. There's not really much that you have to do on paper. You can kind of just do those in your head. Like you can recognize a geometric, a p-series, and nth term. So those are the kind of 3 quick ones that you always want to ask yourself before you go doing anything more complicated, right? Because once you leave nth term test, you will notice that your flow chart gets very arrowy, right? So this is gonna be for the next video, but you spend most of your time series-wise in this area over here. So I want you to notice up here that it says nth term test, are the terms approaching 0? If the answer is no, it's divergent. If the answer is yes, the next term is a little bit of a strange question. It's, does the series have any negative terms? Okay. In other words, in your series, is there one of these guys? I don't care what this rule is over here. If there's one of these guys, then your series has negative terms. And the thing is, there are 4 tests in this big rectangle over here that I mentioned that you're going to spend a lot of time in. Not a one of them can handle a negative term. So if you have any negative terms, if the answer is no, I don't have negative terms, cool, off to the big rectangle you go. If you do have negative terms, notice this where we go. We make like a little pit stop at this rectangle, and then it sends us into the big rectangle. And what this rectangle tells us to do at our pit stop is, yeah, those negatives, get rid of them, throw them away, which seems like kind of not okay to do, right? But here's the idea. If we have a series that alternates, so let's try this guy. Okay. If I write out a few of these terms, let's see, I'm going to make this, don't mind me. So it's going to be then a minus 1, so let's see, a 1, and then a 2 is going to be a 4, and then a 3 is going to be a 9, and then a 4 is going to be a 16, and then a 5 is going to be a 25. Okay, so if this series, obviously you can see here, has some negative terms, right? Well, I can't take negative terms into my rectangle. Most of my tests won't handle negative terms, right? So what they tell us to do up here is throw away those negative terms. Now I want you to see what the effect of throwing away those negative terms is. Right now, your terms are, half of them are being added and the other half are being subtracted, right? So I think of this as like, this guy takes me a step forward, this guy's a little step back. This guy's a step forward, this guy's a step back, this guy's a step forward, the next guy's a step back. So when you start thinking about partial sums and adding things up, convergence here would be if this sum came out to something finite. In other words, we would consider this to be a convergent series if when you add all infinity of these terms, you get something finite. So the idea is this. I can come into this series and I can say, you know what? I'm throwing away this part. I'm taking the absolute value of the series. I'm going to throw away that alternating part, the negative one to the end. What I effectively do is I come in here and I change all these minuses to pluses, right? So instead of a step forward and a step back, it becomes a step forward, a step forward, a step forward, another step forward, another step forward. The idea is this. If you can take all those steps back and change them to steps forward, and it still comes out finite, in other words, if the absolute value of the series converges, then you know the original did. Because if adding them all still doesn't get you to infinity, then certainly if you subtracted half of them, you wouldn't get to infinity. So the idea is this. I have a bunch of tests that are really, really handy, but they have one problem. They can't handle negative terms. So if we have negative terms, the first thing we do is we pitch them and we test the series this way with all the terms added in. If I have convergence, then I'm happy. I say, okay, well, the absolute value converges to the original guy converges. I'm good. If it doesn't, then we have more work to do, right? So you'll notice that it bounces you into this rectangle. Does the absolute value converge? And if it does, great, we're done. But if it doesn't, then we have a little bit more work to do. It's not the end of the road, but we have more work to do. Okay, so I'm having a lot of trouble finding my mouse today. Oops, sorry. So, gist of this slide. You're always going to ask yourself those three quick questions. Is it geometric? Is it a p-series? Is it nth term test? If those don't work, the next step is always, always, always to eliminate those negative terms and test for convergence. I say it's getting tricky because I think that is a pretty tricky thing to do, right? Is to eliminate those terms and test for convergence. The big rectangle, that's where all the good tests are. That's where all the good tests are. All right, so we will talk about those tests in the next section because there's a lot to that. But before we go, I want to talk a little bit about when we go into the big rectangle, what we're testing for. Okay, so again, they require no negative terms. So we're testing the absolute value there. Because we're testing the absolute value of the series, what we say is that we are testing for absolute convergence. That means literally convergence of the absolute value. It's not like, whoa, absolutely convergent. It's not that kind, but it kind of seems like it is. So we throw them away, we throw away the negatives, and it converges. Then we say that series converges absolutely. So in other words, even if I take the absolute value, that sucker still converges. We say that series converges absolutely. Okay, that's important. If you use a test in the big rectangle, what you have tested for is absolute convergence. If you would like, you can go to your big rectangle and write on there that you are testing for absolute convergence, like maybe up here somewhere. Testing for absolute convergence, right? Only if it passes a test in there, we say it's absolutely convergent, that it converges absolutely. Okay. Here's the deal. Again, if the absolute value converges, then the original series does. But it's really important to note that that does not work the other way. If the absolute value diverges, I don't know anything about I don't know anything about the original series. It's also too that if the original series converges, I can't guarantee that if I take the absolute value, it still will. Perfect example, this harmonic series. So this guy we said is called the harmonic, right? And the harmonic series diverges. This guy over here, notice it's harmonic with one exception, -1 to the n plus 1. This guy is called the alternating harmonic series. I have no idea what just happened. Okay. That's called the alternating harmonic series. Well, guess what? The alternating harmonic series converges. But if you take its absolute value, not so much. Okay, so this guy does not converge absolutely. He does not have absolute convergence. This series converges, but if you take its absolute value, it doesn't converge anymore. Okay. So it doesn't work both ways. We have to be really careful with that. So if you take the absolute value and you test it and it converges, we say the original series converges absolutely. If you test that series and it doesn't converge, then we have more work to do. Okay, so in the next video, I will show you what test is in that big rectangle. The great news is that you will notice this big rectangle used to have 4 tests in it, but for 2020 and 2020 alone, you luckies, they have taken out 3 of the 4 tests from the big rectangle, which means that if you get a series that isn't geometric, that isn't p-series, or doesn't fail the nth term test, you're only left with one option. So this sucks for a lot of reasons, this whole situation. This is what we call a silver lining, boys and girls. You're only left with 1 test in the rectangle. That is the best news ever. So I will do the next section. We will talk about this ratio test. It's a really awesome test. It tells us a lot. We'll do a couple practice problems. We'll do more than a couple practice problems with the ratio test. And then we'll finish out your flowchart. Okay, for now, think about absolute convergence, and I'll see you soon.